So in this video, we're going to be looking at a special inequality that will be really useful. So this inequality is going to be called the Cauchy-Schwarz inequality. Okay, and what this says is if we have a bunch of numbers a1, a2, all the way to an, as well as b1, b2, all the way to bn, and they're all real numbers, then we can say that a1 times b1 plus a2 times b2 all the way up to an times bn, and we square those sums, that's always going to be less than or equal to the product of the a's, the product of the sum of a's squared, and the product of the sum of b's squared. And so this is really useful, and the proof is very nice. So the proof, we can say that for any x, we know the following. So just consider this quantity. We're going to say that a1 times some value x plus b1 squared, and then we'll take the other a2 times x plus b2 and square it, and we're going to keep doing that all the way to an x plus bn and square that. And this quantity is always going to be non-negative, so greater than or equal to 0. And just as in a little aside over here, if I were to take a1x plus b1 squared and expand that out, we can write that as a product of two things. And what I would get is I would get a1 squared x squared plus 2, it would be a1x times b1, so 2a1 b1x, and then plus b1 squared. And if we expand, I'll put it in, we'll do red. So if I expand every single term, so right, I just expanded this term, that equals this. That equals this right here. And if I expand this term, it'll look just like this term, but it'll be, a2 squared instead of a1, 2a2 b2x right over here instead of, 1s right here. And that's going to be kind of the method here. So we're going to expand all of those, and we can group them together. And what I mean by that is we're going to have a bunch of a1 squared x squareds, and then a2 squared x squareds, and then a3 squared x squared, and we can write all the way to an squared x squared. And same thing with the middle term, right? If we expand all these out and sum them together, right? If we sum them together, we're going to get a bunch of 2 a1 b1x plus 2 a2 b2x plus 2 a3 b3x, right, all the way to, just put a sum here, 2 a n b n x. And similarly, on the last part, we'll have a bunch of b's squared, so we're just going to have b1 squared plus b2 squared plus b3 squared all the way out to bn squared. And the nice thing is we're summing all of these values together so we can put them together. And what I'm going to do is note that we have an x squared in all of those terms, so I'm going to factor that out. We should also note that I have a 2x in all of these terms, and we're going to factor that out. And there's nothing to factor out down here. So what we can say is once we expand this out, we can say that this is equal to a1 squared plus a2 squared, right, plus all the way to an squared, and I'm factoring out an x squared, right? I'm factoring out the x squareds that were right here. So that's where this comes from. And we were adding all of those, so I'm going to add the next term that we're going to group. And what I'm going to do is I'm just going to put a 2 out here. And we have a1, b1, a2, b2, a3, b3, right? So we can sum all those. So we're going to have a1, b1 plus a2, b2 all the way to an, bn. And again, I'm just going to factor out the x. I'm just going to put it over on the right side just to be consistent because I'm going to be using some quadratics here. So I want to make it look like quadratic. And finally, we're just going to throw the b's. There was nothing to factor out, but we'll group them together. So we're going to have b1 squared plus b2 squared all the way to bn squared. That should be squared right here. So that's the same thing. And we can just condense this. So we can let, I'll highlight it right here. We can let this quantity, we'll call that capital A. And we'll call this quantity, not including the 2, we'll call that a capital B. And we'll just call this capital C. So what we have here is we just have ax squared plus 2, right, bx plus c. Okay, now we have something that looks like it's something we can work with. And recall, we'll say since y equals ax squared plus 2bx plus c is strictly, or not strictly, but we can say non-negative, right? Because our assumption at the top was this right here. So all we did is we rewrote the original expression and we just kind of condensed it. So we still know that it's a non-negative quantity. So we know that y is going to be non-negative for any value x. Okay. And in fact, we also know that the equation, so if we set it equal to 0, so we'll say also the equation and we'll put on the next line. So the equation ax squared plus 2bx plus c is equal to 0. So this equation cannot have two distinct roots. Why? Why can it have, or why can it not have two distinct roots? Well, this is either, instead of crossing it out, this is 0 or greater, right? So if, again, you want to think of it as a graph like we did, move it down just a little bit. You want to think of it as a graph. Whatever this parabola looks like, it's going to be resting on the x-axis or above it, right? Because y is either 0 or greater. So y is either something like this, something like this, something like this, or it can be touching the x-axis only in one spot, something like that. But we cannot have we can't have a graph that, I don't know, looks something, let me choose a different color. We can't have it look like this, because that would mean that we have, for some values x, we would be negative, and that would go against our assumption. So let me not go too far. So we cannot have two distinct roots. We can only have one or no solution. So therefore, we'll continue writing the proof. And this shouldn't be a question mark. Now I'm thinking about it. I was asking myself. It's not a question, it's a definitive statement. There is only one solution or there are no solutions. So therefore, we have that 2b, right, the middle term, squared, minus 4ac. So we're looking at the discriminant from the last video. So the discriminant is either 0 or negative. Right, recall that if d is less than 0, then there are no real solutions. If d equals 0, then there is one real solution. So we're going to use that idea and say, okay, well, then the discriminant has to be 0 or negative. So if we have this assumption right here, then we can isolate b squared. So we get, we'll get 4b squared minus 4ac less than or equal to 0. We can, by our second axiom, going way back to those axioms, we can add the 4ac to both sides. And if we do that, we will get, it's starting to like slant a little bit. I'll try and straighten it out. So we're going to have 4b squared is less than or equal to 4ac. And we can just, I'll note that this is by axiom 2. And I'll move this down a little bit more, using up a lot of space here. And by our third axiom, we are allowed to multiply both sides by a non-negative. So we'll multiply both sides by 1/4. Right, and what's going to happen is both of these are going to cancel. And we're just left with the fact that b squared is less than or equal to ac. And this is what we had to prove. So if we look at the top, we'll scroll back up. So at the top, right, this is just b, and then it's being squared, right? So b squared is less than or equal to this quantity right here is just right here, big A, capital A. And this quantity here is what we define as C over here. So therefore, by our assumption, we have essentially b squared is less than AC, which really is just this giant inequality. And we're going to call it the Cauchy-Schwarz inequality. So the proof is very, it's very messy at the beginning, but it turns out to a very elegant solution just because we know certain things about quadratics. So just to reiterate, what we did is we took this, for any value x, we considered some special quantity right here. And there's no real meaning behind this. It's a nice proof that gets us to our solution. So if we consider that inequality, we can expand it a little bit, and we can get basically a quadratic with 3 terms, rewrite it into something much nicer. And then once we have that quadratic, we know that since the original quantity, right, was greater than or equal to 0, then that means that our quantity that we end up with also has to be greater than or equal to 0 for any value x that we choose. So that means we can't have 2 distinct roots. We can only have one or no solution at all. With that information, we can say that the discriminant must be 0 or negative, and we can just solve for b squared, and it turns out that b squared being less than ac is exactly this inequality at the top, the Cauchy-Schwarz inequality expanded. So I know that was a lot, but I think it's a pretty good proof, and the Cauchy-Schwarz inequality is going to be fairly useful. We will have other inequalities that we'll look at that we'll use for now, but just know that since we've proved the Cauchy-Schwarz inequality, we can use it in the future. So in the next video, we'll be looking at some exercises, and then we'll be looking at irrational numbers.